relative flow. And typically when you see this type of stuff here, does everyone remember what relative flow is? Okay, yeah. Basically what we do is we put a drop of our radiopharmaceutical that we call the origin, and then we put it in the solvent, and then the solvent moves up to a certain distance. You put it in for the same amount of time, and this up here is called the solvent front. And then you measure the distance, and if there's anything that's free, or usually like, well, in system 1, anything that's free moves with the solvent front. So this would be like your sodium chloride here. Okay, so your free technetium would be here, if there is any. But we also do it with just the technetium by itself, because we want to know where the technetium is going to go. So, for example, in the system 1 over here, okay, in system 1, the distance that it travels from the origin to up here is the same. So, basically what's going to happen is when you cut this in half, all the free technetium will be up here, and all of the labeled stuff will be down here. So you should have the same relative flow number with the technetium every time you do it. So the radiopharmaceutical, I'm sorry, what they're saying here is that the technetium MDP should be down here and not move at all.
What's the solvent there? Is that saline? Or
yeah, it's the 0.9, it's just normal saline. And then this would be system 1. And then system 2 is the same thing. Except normally we use things like acetone or something else in here to, you know, for this other thing. And in this one here, the hydrolyzed reduced technetium doesn't move, and your technetium MDP does. So it's just the opposite. Okay. But on this thing here, okay, we measure the distance that the technetium travels from the origin to the solvent point. So for like the technetium here, we measure the distance from here to here. So let's just say that that's 9 centimeters or 9 millimeters, and then the distance from the origin to the solvent front is 10 centimeters. Okay, so the relative flow for the technetium should be 9 over 10, or equal to 0.9. So that means every time you do a test for this radiopharmaceutical, the free technetium should always travel 90%, and the radiopharmaceutical itself shouldn't move at all. Does that make sense? That's what the 0 means, that there's 0 movement on that. The free technetium goes to the 90% line up to here. And on a system 1, hydrolyzed reduced technetium does not move either. So it stays in the origin along with your radiopharmaceutical. That's why you have to do the second test for it. And that's what it's saying here. On the second test, okay, your radiopharmaceutical, the MDP, will actually travel with the solvent. So I should actually have the solvent line up here. Okay. So what happens then is the distance from the origin to here, let's say, is 10. The distance from the origin to the solvent front is 10. So therefore, your RF is 10 over 10, or equal to 1. So that means that your radiopharmaceutical moved with the solvent. And that's why on system number 2 here, it's telling you that the radiopharmaceutical is 1, because it moved with it. And then the hydrolyzed reduced technetium here doesn't move at all, it stays at the origin. Okay? It's weird, huh? It's basically just the opposite of using the system 1, so everything is reversed. You notice that the free technetium moves with your radiopharmaceutical, okay, on system 2. And only the hydrolyzed reduced technetium stays where it is. But remember, this is the other thing that you would be expected to know how to perform is how do you calculate what the actual percent tagging is? Okay, we know that for bone scanning agents it should be 95%, right? So what would be the answer to this question here? Okay, did you actually calculate it out, or are you guessing? Okay, that's not the correct answer. Okay, if you remember to do the percent tagging, we normally take those strips and cut them in half. Okay, and plus we also get the background reading too, but I didn't include background in this. So for system number 1 up here, the percent free tagging, or the percent free, okay, and this is the free tech, okay, it's going to be 1716, and then it's going to be divided by 1716 plus 23706. Okay, so basically you have 1716 divided by, what do we have there?
25422.
Was it 2 and 5? Did you get?
I mean, oh, 25422.
25422. And it should be like about 5 or 6% or 4%. What'd you get? So 6%? 0.06, did you multiply it times 100?
Yeah, 6%.
Okay, and then we do the same thing with the one down below here, okay? But in this case here, this is what they call the hydrolyzed reduced technetium, or technetium dioxide. This is technetium that's combined with electrons that have been removed because of the radiation exposure. Remember, radiation ionizes and causes free electrons to be released. So in this particular case here, this normally will stay on the column. It does not get eluted. You know, that's why you only have like an 80 to 90% elution efficiency. So about 10% of the technetium just stays on there. So we got to go through the same thing here. And on this particular case here, it's going to be 1200 over 1200 plus 21001. Okay, so it works out to about maybe 11% or another 4 or 5% here.
5.4.
Okay. So 5.4%. Okay. So the combination, normally hydrolyzed reduced technetium will just stay in circulation. It interferes with your ability to have the radiopharmaceutical concentrate. So it ultimately winds up affecting the contrast of the image. Okay? But you need to add both of these together to find out what the percent tagging is. So in this case here, it's about 11.4. So the answer, I think this one should have been a little bit higher.
6.75.
Okay, so 6.75. Okay, because the answer actually should have been B.
E.
Yeah, because you add both of these together, it's about 12%, 12 point something
12.1.
percent. How much?
12.1.
Okay,
Minus 100.
and you subtract that from 100. Excuse me. Okay, so in essence then this batch of technetium should not be used. Okay, it's got poor tagging characteristics. And that's what number 2 would have been. Can this radiopharmaceutical be used? No. Okay,
Why?
remember we have to have 92% or higher tagging. Okay. Now the free technetium, remember this is stuff that goes to the salivary glands, the stomach, the thyroid. The hydrolyzed reduced, it just stays and sort of blends in. Now, if you have a kit that has a lot of tin chloride in it, then this hydrolyzed reduced technetium will combine with that and actually form a particulate that gets filtered out by your liver, spleen, and bone marrow. So this will actually give you a bone marrow, like a liver spleen scan. Okay? And then one of the other questions that's not on here, but I did ask, is preparing kits. Okay? So let's say that you milk the generator at 8 a.m. You get 800 millicuries and you use 10 ml. Okay? Just so you know, if you need to have a certain concentration, now what's the concentration of this right now? What's my specific concentration?
80 millicuries per ml.
Okay, it's 80 millicuries per ml. Okay? If I used 5 ml or I used 20 ml, I'm going to get the same 800 millicuries. But if I used 5 ml, this would be 160 millicuries per ml. If I use 20 ml, this would be 40 millicuries per ml. So depending upon how much volume and what concentration you need for your kits, that determines how much saline that you use to pollute the generator. Okay? Does that sort of make sense? Because this, so one of the questions that you'll likely see, and I'll probably throw 1 or 2 in as a bonus on the quiz next week, but I'll ask you for calculating specific concentration. Okay. Then the next thing is, okay, you've got patients that are coming at 9 a.m., 10:30 a.m., and 12 noon. Okay? So, you're going to prepare your dose at 8 a.m. in the morning. Okay? But you want to make sure you have enough activity so that this person coming at 12 noon will have 20 millicuries. Okay? So you want to give 20 millicuries here, 20 millicuries here, and 20 millicuries here. So the question would be, how much activity do you have to make in your kit at 8 o'clock in the morning to ensure that everybody here gets the dose that they need?
What's the decay factor again for?
Okay, well, the 1 hour decay factor is 0.89. The 30-minute is 0.94. Okay? Now, in Ann Steve's, they talk, if you wanted a general amount of activity, you could add all these together. You've got 60 millicuries, and you could use a decay factor of 4 hours. And by using a positive decay, that would give you an estimate. But that isn't the actual activity that you would use. That's just a ballpark figure. So method number 1, okay, you need 60 millicuries at 12 noon, which means, okay, our technetium is going to be, the activity is see, what are we gonna need here? 60 millicuries, and then we're gonna have to pre-decay it down. So, 0.1155 times 4 hours. Okay, that's going to be 462.462. Let me just get the calculator on here again. So, 0.1155 times 4 hours equals for some reason, oh, I see what's happening here.
Should be 37.
No, 0.462. I'm having a problem with my calculator here. For some reason, it's giving me my answers in degrees, and I'm not looking for degrees.
You want to use my calculator?
I'm trying to figure out why this one is acting up on me here.
This is bad. But not at all. Hey, you.
I didn't want it to say what I did here. Okay, 462. Okay, so for 4 hours, the decay factor would be 0.63. So basically, if you had 60 millicuries divided by 0.63, that would tell you how many millicuries you need.
.95.
Okay, so that's a ballpark figure. But the correct way to actually do it would be this. Okay, you have 20 millicuries, and you're going to divide it by 1 hour decay factor of 0.89. On this one here, you've got 20 millicuries, we've got 2.5 hours post-decay. So here's 0.89 for the first hour, multiply that times 0.89 for the second hour, and then multiply that times 0.94 for the half hour. Okay? And then with this one here, 20 millicuries, okay, we've got 4 hours, so this is just going to be 0.89 times 0.89 times 0.89 times 0.89. What we basically did, this 0.89 comes from the decay factor that we calculated over here. So if you had 100 minus 0.11 equals 89. So this, if you add all these up, this would tell you the actual amount that you would really need to do this. Okay, so 20 divided by 0.89 is probably about 22. Is that what you get, 22 millicuries? Okay, so 20 divided by 0.89. Okay, so 22.4 millicuries for the 9 o'clock dose. And then if we divide that by 0.89, that by 0.94. Oh, how the hell did that happen?
26.86.
Yeah, I don't, we had 22.4. You divide that by 0.89. That's what I did. What is that? Is that multiplication down here? Subtraction. Okay, that's what I did wrong. Okay, and then you divide that. And then you divide that again. 0.94. Okay, so you actually needed about 30 millicuries for the second dose. What did you get?
I got that. Was that for 10:30 over 12 o'clock?
For 10:30, I got 30.4. Okay, and then
I get that.
well, let me check again. I'm not real comfortable with this computer right now. Okay, we had 20 millicuries for 8 o'clock, and then we're going to divide that by 0.89.
So that's 9 o'clock.
So there's 9 o'clock. Then divide it again by 0.89.
It's 10 o'clock.
Okay, there's 10 o'clock, and then divide it by 0.94 for the 10:30.
26 points up.
Okay, 26.8. Okay, and then I'm just going to multiply that times 0.94 for just to get it back to where we were before. Okay, so we had 25. So now I'm going to divide it by 0.89 again, 2 more hours. Okay, so you need 31.8 millicuries for the 12 o'clock dose. If you add all those together, 48, 49.2. Is that the plus?
81.
Yeah, that's the plus.
That's a plus?
Mm-hmm.
Okay. 49.2. So 81 millicuries, is that what you got, roughly? You will see questions like this, where they'll have you calculate how much you need to draw up.
Are you going to give us the decay factor? Or?
Yeah, but I mean, that's something you should, for technetium, just as you say, if you want to pre-calibrate it, you can either divide it by 0.89 or you can multiply it by 1.11. Either way.
So is that a constant then?
Yeah, for technetium.
And the half hour was 0.94.
Yeah.
How do you find the decay factor again? It's just
0.693 divided by the physical half-life. So 6 hours is 0.1155 for technetium. Then I subtracted that from 100 to get the 0.89. Okay?
And just to double check our work, we could use the Beer-Lambert law
Yeah,
and
so I was
plug
going to
it
say,
in and go back
probably be easier.
to get our 20 millicuries
Yeah.
at the time of use.
Yeah.
Cool.
Okay, so with that being said, next week we will have a quiz over the skeletal system. And I will have some problems like this on here. There'll be bonus problems though. I want you to, so take a look at the radiopharmacy section of Leanne Steves so that you can refresh your memory on what relative flow is and what, quality control calculations would be. Okay? Why does it look so dark here? feel like the Dark Lord. Okay. Now, in the stuff that I sent you for PowerPoints today, we're going to move on to our next section, which will be lung scanning.
Is this the Delta quiz you were talking about?
That's going to be part of it. But I sent you a sample copy. It's about 63 questions, and with the answers. Did you all get that? Ashley, Singh, you both got those?
Yeah. Should have gotten all of them.
You sent it to us this morning?
Yep. Oh, no, the skeletal one I sent before that. That's probably a couple of weeks ago.
Plus.
What are you, Irish? In Ireland, you sell, I forgot how much it was.